Hello, and welcome to the tutorial of the Virtual MEM Computing Machine SaaS platform that will cover the use of the Dynamic Parameter Search Mode to find parameter distribution for a given family of problems using the Monte Carlo algorithm. We'll then demonstrate how to use these new parameters as starting boundaries when running new jobs in order to accelerate the search for optimal parameters for the circuit. To do so, let's go ahead and create a new job and select the Dynamic Parameter Search modality. Here, we provide the name for the job. Let's call it RMINE11, which is another problem from MIPLib. We can choose between either using a CPU or GPU virtual machine, as well as set up a timeout, which is the maximum amount of time allowed for this job to run. For this example, we'll actually not be setting a timeout, and instead, we'll limit the time it runs through a different parameter, which we will get to shortly. Here, we're going to use a number of Markov chains and CPU cores to use on our virtual machines, which we set at 36, since that is how many physical cores are available. One chain per core is typically the most efficient for CPU virtual machines with a large number of cores. However, the optimal number of cores for a given job is explained in depth in the advanced tutorial that covers the number of cores and Markov chains settings. We can set the simulation time to 5. For an optimal setting of CPU and simulation times, watch the relative advanced tutorial. We can then set the maximum time allowed for each iteration here. It's recommended to give more than enough time when using the Monte Carlo, so we can simulate the full simulation time for each iteration, which is detailed in the advanced tutorial on CPU and simulation time setting. For example, we can set 300 seconds per circuit simulation with 100 iterations of the Monte Carlo. So, to restate, each iteration of the Monte Carlo is one circuit simulation per Monte Carlo chain. Down here, we set the boundaries for each parameter. But because we have no information about the current problem, we leave all of the boundaries open, meaning we put the hard boundaries for each parameter at 0 and 1. At the bottom, we see our number of replicas, feasibility tolerance, and initial objective, which we leave as is. From here, we can upload our problem. In this case, it is RMINE11, and submit the job. Now, because I've already previously run this problem, we can look directly at the results through the API we provide in Python. Once in the API, let's go ahead and run the main file by right-clicking and selecting the Run Main command. This table appears, which displays different plotting options to visually view the results of the job. Since we ran a dynamic parameter search job and we want to see its progress during the Monte Carlo iterations, we can use the iteration view plotters for dynamic mode jobs and select the solver history file for RMINE11, which is the outcome found from our solver. Here, we can examine the results. The x-axis is the iteration number, which reaches 100, the number we set, and for each iteration, here are the results of all of the Markov chains. If we take a closer look at the first one, we can see exactly what each Markov chain did at the first iteration. We can do this for each iteration as well to compare each iteration and see how the Monte Carlo found better and better parameters. We can also review these results another way. If we click the Best in History option and refresh, we can see how each Markov chain was searching for better sets of parameters because the circuit at later iterations is able to optimize further. We can also review the results using the parameter view plotter for dynamic mode jobs. When selected, a plot for each parameter will pop up. In this case, the plots are empty. We can fill these plots with different information. For example, we can plot the histogram of each parameter value from the best 200 outcomes from the Monte Carlo. So, if we refresh the plot, we see those distributions showing where each parameter gave one of the best 200 results. For example, we can see parameter 13 has a good range, around 0.5, because it was approximately that value when all the best solutions were found. So this is a good spot for this parameter, and we can see the good boundaries for all of the others as well. Another way to view the results of the Monte Carlo is to plot the best values obtained for each parameter value. To do so, let's unselect the histogram option and select the OC plot, which stands for Objective Constraints, and refresh. Let's expand this new plot to get a better view. We can see the lowest number of unsatisfied constraints found in blue and the best objective value found in orange. The regions in which we have better solutions from our solver are represented by the lowest objective value found with 0 unsatisfied constraints. For example, we can see that the section below 0.04 is a better region for parameter 2. Besides a mere visualization, we can use information from the dynamic parameter search mode to set up other types of runs. For example, extracting good parameters for the standalone mode, setting parameter boundaries and initial parameter sets for the dynamic solution search mode, or fine-tuning with a second round of the dynamic parameter search. In this tutorial, we discuss how to set new boundaries for the parameters. We can do so by unselecting the OC plot and set the bounds. We have three options when managing the bounds. One way to set the bounds is to use the default setting of the 10 best parameters found as the soft bounds and the 100 best parameters found as the hard bounds. What are soft bounds and hard bounds? The SAS uses the soft bounds to limit the initial values of the solver parameters when starting the Monte Carlo. As the Monte Carlo proceeds, the parameters for each Markov chain may leave these bounds while searching for better parameter sets. However, the hard bounds restrict the range allowed at any time. The default is 0 and 1, and so we are restricting the space of the parameters where we want to search for the solutions. So, we can see that for this Monte Carlo run, we can visualize the good regions and the bad regions that we want to exclude. For example, for parameter 2, the green region is the region within the soft boundaries. These soft boundaries are given by the best 10 solutions found during the Monte Carlo, while instead, the hard boundaries are selected by the best 100 solutions. So the red region means that none of the best 100 solutions were found using this region of parameters. We can, of course, adjust the hard bound settings to see, for example, the best 300 outcomes. And we can play with these settings to better decide how to run future runs using the parameter search mode or solution search mode. We also have the option to select custom parameters to set the hard and soft bounds. For example, we can keep the first 100 parameters to set as the hard bounds and choose specific parameters to set the soft bounds. The choice of specific parameters can derive from previous analysis performed by, for example, using the standalone mode to assess which parameters are actually the best among the ones provided by the dynamic parameter search, as explained in the advanced tutorial on the selection of best parameter sets. I can do this by selecting the By Parameter Set option by my soft bounds, and then down here as well, select soft bounds. From here, I can select the specific parameters I'd like to use to set my soft bounds. As an example, let's select 2 parameters. As we can see, this has now set the soft bounds according to just these 2 parameters. We finally have a third option to modify soft and hard boundaries. Let us consider, for example, parameter 3. If we visualize the histogram of the best 200 solutions, we can see that many of them accumulate at 0, and so do the soft and hard boundaries. We can therefore manually enlarge the lower bounds for parameter 3 by selecting Override Bound and the third parameter, and then set -0.5 for both soft and hard boundaries. We can now see that the plot shows larger boundaries for both soft and hard boundaries, and this will allow the solver to search for optimal parameters that can be outside the boundaries we previously set. We now have the capability to include these new boundaries in future parameter search or solution search jobs. To do so, you can export them in a JSON file to include in a new run or watch the next tutorials to learn how to set them internally and create a new job through the API. Thank you for watching this tutorial using Dynamic Parameter Search Mode. We hope it was informative and answered any questions you might have. For more information on MEM computing, please visit our website or contact us directly at info@memcpu.com.